My name is Muhammad Harizan Hazim bin Harizan. My matrix number is A220312.
Nama saya Nusya Suhaini binti Muhammad Syawal, bernombor matrik A217653.
And I am Nur Syairah Nadira binti Erman, and my matrix number is A216762.
In this experiment, we study isomerism and conformation in organic molecules. Carbon atoms can form many different structures such as chains and rings, which leads to a wide variety of compounds. Isomerism occurs when molecules have the same molecular formula but different arrangements of atoms. This includes structural isomers, geometric isomers caused by restricted rotation in double bonds, and optical isomers, which are mirror image that cannot be superimposed. Organic molecules can also change shape through rotation around single bonds, forming different conformations like eclipse and staggered. These forms have different energy level and stability. Using molecular models, we can clearly visualize these differences and better understand the structure and behavior of organic molecules. This is the material that has been used in the experiment.
For part 1, geometric isomerism of molecules. A model of ethene was constructed. This model cannot rotate. A model of the molecule ethane was constructed. This model can rotate. A model of the molecule ethine was built. This model cannot rotate. All atoms align in a straight line. So, single bond can rotate freely, double bond and triple bond cannot rotate freely. So, the longest bond is ethane. The second model of an ethene molecule was built. Both models of the ethene molecule were superimposed. Two molecular models of chloroethene were made from the two molecular models of ethene above. The two chloroethene models were superimposed. Two molecular model of 1,1-dichloroethene were constructed from the two molecular model of chloroethene above. Two model of the 1,2-dichloroethene molecule were built from the two model of the 1,1-dichloromethyl molecule above by switching the chlorine and hydrogen atoms. For the second model, the two chlorine atom and the two hydrogen atom will switch so that similar atoms will be farthest away from each other. Isomer of molecules. Two molecular model of bromochlorofluoromethane were made. The atom of choice were exchanged in one of the model mentioned above. Two molecular model of chlorofluoromethane were derived from the two molecular model of CHFClBr above.
Conformation analysis of aliphatic molecules. Rotation of ethane model. When one of the bond in the ethane model is rotated, yes, it can be rotated freely because the carbon-carbon bond is a single bond. As the carbon number 1 atom is rotated clockwise while holding carbon number 2 fixed, the spatial arrangement of hydrogen atoms change continuously. However, the overall shape of the molecule remains tetrahedral around each carbon atom. This rotation occurs due to the torsional split, which arises from electrostatic repulsion between electron clouds of the CH bond on adjacent carbon. The molecule rotates to reduce this repulsion and reach more stable arrangement. Eclipse conformation. At a rotation angle of 0 degree, the molecule is in the eclipse conformation. In this conformation, the carbon number 1 with H bonds are directly aligned with the carbon number 2 with H bonds. The Newman projection shows all hydrogen atoms overlapping, which is in parallel lines. One carbon number 2 hydrogen bond is drawn vertical. Name of conformation is eclipse. Number of interacting hydrogen pairs is 3 pairs. Torsional energy per pair is 1 kilocalorie per mole. Total torsional energy is 3 kilocalorie per mole. The distance between hydrogen atoms is minimum, meaning maximum repulsion. Staggered conformation 60 degree. When the molecule is rotated to 60 degree, it becomes staggered. The carbon number 1 with H bond are positioned between the carbon number 2 with H bonds. All 6 CH bonds are clearly visible. This arrangement minimizes repulsion. Rotation angle is 60 degree. Name of conformation is staggered. Number of interacting hydrogen pairs is 3 pairs. Torsional energy per pair is 0 kilocalorie per mole. Total torsional energy is 0 kilocalorie per mole. The distance between hydrogen atoms is maximum, meaning minimum repulsion. The staggered conformation is more stable because it has lowest torsional strength and lowest potential energy. Other rotation angles. As rotation continues, 120 degree form eclipse conformation, 180 degree form staggered conformation, 240 degree form eclipse conformation, 300 degree form staggered conformation, 360 degree form eclipse conformation, same as 0 degree.
Part 4 Procedure. Alright, let's move on to part 4, where we analyze the conformations of alicyclic molecules. We started by building a model of linear hexane, making it as straight as possible, and noting the tetrahedral geometry around the carbons. Next, we connected the ends to form a cyclohexane ring. Right away, we could see that the ring isn't perfectly flat. It naturally puckers to relieve bond strength. From there, we manipulated the ring to test different shapes. First, by holding two opposite carbons and twisting them upwards, we formed our first conformation and observed the internal bonds. Then, we held one side steady and pushed the opposite carbon downward to snap the ring into a second conformation. Doing this hands-on allowed us to physically identify the chair and board shapes and directly count the staggered or eclipse ethane, like bonds within the ring, to judge which shape felt more stable. Now let's move on to our findings for this experiment. Finally, let's hear for our discussion and conclusion. So, what did all these models actually show us? Let's break it down. In part 1, we observed that single bonds can spin freely, but double and triple bonds lock the molecule rigidly in place. That restricted rotation in double bonds is exactly what creates geometric isomers, like the distinct cis and trans version of 1,2-dichloroethene that we built. Moving to part 2, we focus on symmetry. We proved that if a molecule lacks a plane of symmetry, like bromochlorofluoromethane model, it forms a non-superimposable mirror image, meaning it has an enantiomer. But if it possesses a plane of symmetry, like chlorofluoromethane, the mirror images stack perfectly on top of each other, making it optically inactive. In part 3 and 4, our focus shifted to torsional strength. With our simple ethane model, we saw that twisting the bonds creates different energy states. The staggered conformation is the most stable because the atoms are spaced out, minimizing repulsion. In contrast, the eclipse form forces the electron pairs close together, creating maximum strain. We applied this exact same logic to our cyclohexane ring. The reason this ring occurs into the chair conformation is that it forces all those internal carbon-carbon bonds into a staggered arrangement. This keeps the torsional strain incredibly low, making the chair significantly more stable than the bond conformation, where the bonds end up eclipsed. To wrap things up, this experiment really highlighted how a molecule's three-dimensional geometry dictates its property. Whether we are dealing with structural, geometry, or optical isomers, the physical connectivity and symmetry of the atoms matter immensely. But the overarching rule we observe today is that molecules will naturally shift and rotate the single bonds to find the most comfortable shape. Ultimately, conformational stability is all about minimizing electrostatic repulsion and torsional strain.